think we'll start. So we're very pleased to have Mario Trigiante. How do I pronounce that, Mario? Is that okay? Here,
Yes.
who's going to tell us about his S-fold program. We don't normally do long introductions, but I feel obliged to say that Mario really is an expert in supergravity. Yeah, we're very pleased to have him. So please go ahead, Mario.
Okay, so thank you, Kevin. Thank you very much for inviting me to give this seminar. So this talk I will discuss some recent development, some progress in the study of this kind of solution called S-folds, which are non-geometric and non-perturbative solutions to superstring theory, particularly to type IIB superstring theory. Okay. What I'm going to talk about is contains.
Oh, we seem to have lost you, Mario.
Sorry?
You muted yourself for a second.
Oh, okay. Okay, can you hear me?
Yeah.
Okay. Yes. Just tell me, because my internet connection is not really ideal. So in case, just stop me and I will resume. I will stop for a while. So this program also involves a student of your university, Anik Rudra, in this recent work, which I've been discussing with him and with Kevin. Let me start. I will start by giving general introduction, some general motivations as to why considering this kind of solution is interesting. Then I will focus on discussing S-fold solutions in type IIB. I will review how they have been originally constructed, starting from four-dimensional maximal supergravity. Then I will move on to the discussion of a two-parameter class of non-supersymmetric deformation of the most important S-fold solution, which is the half supersymmetric, half maximal solution, n = 4 S-fold solution. Then I will move to the description of the three-parameter class of deformation of the same solution. Then, if I have time, I will also briefly mention some recent results on the study of S-fold black holes, that is, black hole solutions asymptoting S-fold backgrounds. And I will end with some concluding remarks. So let me start with a very general introduction. Superstring theory is widely acknowledged to be the most promising candidate, one of the most promising candidates for a fundamental unifying quantum theory of the fundamental interactions. Okay. Now, this theory, it is reasonable to expect this such a theory, such a microscopic description of the fundamental interaction, to be unique. However, there are more than one superstring theories. No? Now, this seeming conceptual problem has been solved in the 90s with the second string revolution, with the discovery of the so-called superstring dualities. Now, this concept, the concept of superstring dualities, will be central in my talk. So I will start from this. By superstring duality, we mean correspondences between different superstring theories on different backgrounds, in light of which these theories can be regarded as different descriptions of a same microscopic degrees of freedom, or a same quantum physics. Okay. Now, the existence of these dualities, these correspondences, allows us to think of these different superstring theories as different effective descriptions of a same yet unknown quantum theory, which was which was proposed originally in the 90s to be M theory by Edward Witten. And it is reasonable to expect that these dualities, which are equivalences or correspondences between different superstring theories, to be exact symmetries of this underlying microscopic theory. Now, superstring theory is not a local field theory, since it describes an extended objects which are oscillating strings. However, in the infrared limit, the low energy dynamics of these superstring theories is described by a field theory. This field theory is supergravity. Supergravity as defining symmetry principle. Now, different dual superstring theories are described in the low energy limit by the same supergravity. So dualities intended as correspondences between different superstring backgrounds, okay, are mappings between solutions of a same or equivalent supergravities. Namely, superstring dualities manifest themselves as global symmetries at the level of low energy supergravity. Now, this is an important point because this is the way they've been studied. I mean, originally studied, and in light of this, Townsend and Hall in '94 conjectured that all or most of the known superstring dualities were encoded in a large group, a discrete group, which was a discrete version of the global symmetry group of a certain theory, which is a maximal four-dimensional theory. Okay. Please interrupt me if there's something, if you have any questions. Okay. Now, this feature, makes supergravity theories a privileged framework for studying string dualities, no? Because the string dualities are global symmetries, and they are part of the mathematical description, mathematical features of the supergravity theory. Okay, and in particular, they are a privileged framework for constructing these special solutions, which will be at the center of our discussion, which are the so-called S-folds, which lie in the intersection between dual string theories. Okay, S-folds were originally conjectured and well in these papers by Hall and Cataldo-Zer. Now, what do we mean by S-folds? How do we characterize this special kind of solutions? These backgrounds encode string dualities as a built-in feature encoded in their space-time structure. By this, we mean that as we move along moving space-time, okay, the background fields undergo a duality transformation, okay? To be more precise, S-folds are non-geometric backgrounds in the sense that one needs more than one space-time coordinate patch to describe such backgrounds. And on overlapping patches, the transition functions not only implement the effect of diffeomorphisms or gauge transformations, as it would be the case for ordinary geometric backgrounds, but they also involve duality transformations. So duality transformations are part, if you want, of the so-called structure group, okay? Now, maximal n equal 8, so maximal supergravity in four dimensions, and by maximal I mean supergravity in 4 dimensions, which has the maximal amount of supersymmetries allowed for a local theory of gravity, okay? And that corresponds to n equal 8 in 4 dimensions, namely to 32 supercharges, okay? So maximal supergravity in 4 dimensions has provided a valuable framework for constructing and studying in general backgrounds of solutions of type 2 or M theory of the form of a worked product of a 4-dimensional non-compact spacetime, okay, and an internal compact spacetime, which is intended to be very small. And 4 denotes a maximally symmetric solution of the 4-dimensional model, that is 4-dimensional maximal supergravity. Maximally symmetric means that it admits the full Lorentz group as an isometry group. We will consider geometries of the form of the anti-de Sitter kind, okay? So for us, M4 will be 4-dimensional anti-de Sitter, okay? Now, as a solution to the 4-dimensional theory, this background, that is M4, this geometry, this 4-dimensional anti-de Sitter space, okay, is defined by setting all the spin 1 and spin 1/2 fields to 0, okay? This is related to the condition, follows from the condition that the background be maximally symmetric, okay? While the scalar fields are allowed to be non-vanishing, okay, but they have to be constant, okay? They're set to constant values, uniform values, okay, space-time independent values. And these values, they are defined by the condition that a scalar potential, which is characteristic of the 4-dimensional model, okay, be extremal. So the scalar fields are fixed to some extremal points of the scalar potential, okay? Now, it may happen that these extremal points are not isolated, but are aligned, as in this picture here. They are aligned, okay, in some flat directions of the scalar potential, okay? This is the case we will be considering. Now, as you well know, anti-de Sitter spaces are relevant because of the ADS-CFT correspondence. No, supergravity or superstring theory in general realized on a space of the form ADS times and some internal manifold had been conjectured to be dual to some non-gravitational theory, okay, defined at the boundary of the 4-dimensional space, 4-dimensional anti-de Sitter space. Now, in this picture, in the holographic picture, flat directions of this kind correspond to exactly marginal deformations of the conformal field theory at the boundary, okay? Now, this approach for constructing 10 or 11-dimensional solutions starting from a gauged 4-dimensional supergravity is particularly useful for those backgrounds which have a small residual symmetry as the backgrounds we are going to consider. Because in this case, constructing them directly in higher dimensions would require solving non-trivial partial differential equations, while their construction at the level of 4-dimensional supergravity, okay, reduces to an extremization, reduces to extremizing a potential, a scalar potential, that is an algebraic problem, okay? So this is the main reason why this approach is so valuable. Now, this model, this gauge supergravity, defines a suitable consistent truncation of the low-lying modes, of the low energy modes of the superstring or M theory, okay, that is 11-dimensional supergravity, on the background geometry, okay, of this characterized by this internal manifold. And the geometry of the internal manifold is encoded in the gauge group, internal gauge group, defining the gauge supergravity, okay? And also in the point of the scalar manifolds, which defines the extremum of the scalar potential. Now, the gauging itself, namely the structure of this group, this gauge group, defines the topology of the internal manifold, as we will see, okay, and totally fixes the scalar potential. Now, the fact that this is a gauge supergravity is derives from the fact that extended supergravities, and that is supergravities with more than 8 supercharges, okay, can be endowed with a non-trivial scalar potential, that is non-trivial dynamics for the scalar fields, only through the so-called gauging procedure, namely, which consists in promoting a suitable global symmetry group of the action to local symmetry group, okay? And when we consider gauge supergravity describing suitable consistent truncations of type 2 superstring theories or 11-dimensional supergravities compactified to 4 dimensions, well, this gauge group comes automatically, and it is related, as I just said, to the geometry of the internal manifold and or the fluxes, internal fluxes, which are present in the background. Now, the embedding tensor formulation of gauge supergravity and the discovery of the so-called dionic gaugings, okay, allowed the recent construction in the last 15 years or so, okay, of the 4-dimensional effective descriptions of a number of new string M-theory vacuum, okay? Now, once this a vacuum is constructed in a 4-dimensional theory, no, then we have the problem of uplifting it to 10-dimensional superstring theory or 11-dimensional supergravity. Now, to this end, exceptional field theory provides a direct embedding of certain gauged maximal supergravities in type 2 superstring theory or 11-dimensional supergravity. So it has proven to be a very valuable tool for uplifting solutions, extrema of the potential in the lower dimensional theories to fully fledged 10 or 11-dimensional solutions. And moreover, it also allows to compute the Kaluza-Klein spectrum on solutions for which conventional methods for computing Kaluza-Klein spectrum would not really apply, okay? Now, we will focus on a particular gauged supergravity, maximal supergravity in 4 dimensions, which I will refer to as J-fold model. The gauge group in this case has this form here. It has an SO6 times SO11 part, okay, with a semi-direct product with 12 translations, okay, translational transformations, okay, which are generated by nilpotent generators. Now, this gauging, so this gauge group is strictly related to the kind of solutions that this model describes. This model was embedded, the whole model was embedded into type 2B through exceptional field theory about 8 years ago, okay? And all the solutions of this model were uplifted to S-fold solutions, or better J-fold solutions, as we shall see, okay, to type 2B superstring theory, okay? So this is the framework we will be working in. This is the theory we will be working in. So let me first recall a few facts about type 2B superstring theory. It is described in 10 dimensions, okay, in the low energy limit by a 10-dimensional maximal chiral supergravity, the duality group of this theory is SL2Z, okay? Which I will denote by SL2Z type 2B. The bosonic sector consists, besides of the matrix, of an axionic field, C, and a dilatonic field, which combine in a complex field, spanning a scalar manifold, which is SL2R over SO2. Now, the points of this manifold are identified by the action of the duality group, okay? So this is the quantum modular space. Now, this also defines how duality acts on these fields, okay? So these fields are not inert under duality, but the duality acts according to this characterization here. While there are also Nevers-Schwarz, and Ramon-Ramon two forms, okay, which combine in a doublet with respect to the SL2Z duality group. Finally, there is a Ramon-Ramon four-form field whose field strength, which is defined in this way, okay, is self-dual. And this is an SL2Z singlet, so it does not transform under the duality group, and it does not couple to the dilaton as well. So let's come back to our four-dimensional maximum supergravity with this gauge group, okay? Now, all the vacua of this theory, of this model, are uplifted to S-folds, which have this general structure. I mean, they have, as I said before, they feature a four-dimensional non-compact anti-de Sitter space, okay, times an internal compact manifold, what I referred to before as M-int, okay? Now, the internal manifold, which is a six-dimensional manifold, is the product of an S1, okay, a circle times a manifold which has the same topology as a phi-sphere. So it can be seen as a deformed phi-sphere. Now, there is something special about this circle. There is a monodromy associated with this circle, so that as we move around this circle, namely, we vary its coordinate, which I denote by eta, by the length of the circle, which I denote by t, okay, all the fields are transformed, are acted on by an element of the duality group of type 2B superstring theory, that is SL2Z, okay? So the monodromy associated with this S1 is an element of SL2Z. More precisely, it is an hyperbolic element of SL2Z. And this is related to the definition, to the very definition of our model, okay? In particular, it is related to this SO1,1 factor here. The fact that this element is hyperbolic. And therefore, we can always bring it to coincide with the representative of one of the infinitely many conjugacy classes, okay, of hyperbolic elements in SL2Z. These representatives are denoted in mathematical literature by Jn, and they are defined in this way. Namely, this is their representation as an element of SL2Z, okay, where they depend on this n integer, and n has to be greater than 2. Because this representative is denoted by J, all these spaces are called J-folds. So they are special kind of S-folds, which we denote by J-folds. Now, Kevin, are there questions?
Not at this point. Any questions?
Okay, no. Okay. I was afraid of having missed some. Okay, so let us proceed. Now, why are these solutions so special? So why should we really be interested in such weird solutions, which contain in their very definition and the structure of space-time string dualities? Well, first of all, the half maximal solution so this gauge supergravity admits a solution that is a vacuum which preserves 16 supercharges. So it's called half maximal solution. So it's an n=4 vacuum, okay, that uplifts to a J-fold in type IIB superstring theory, preserving 16 supercharges, okay? Now, this vacuum solution in 4 dimensions is somewhat special because it is the second most supersymmetric vacuum in any maximal 4-dimensional supergravity, okay? The first most supersymmetric solution is the n=8 vacuum, which describes the compactification of the Freund-Rubin compactification of 11-dimensional supergravity on ADS4 times S7, which is and it is a vacuum of the SO8 gauged supergravity. The second one, the second most supersymmetric vacuum, is precisely this one, okay, and it uplifts to an S-fold. Now, as a consequence of this, pure n=4 supergravity in 4 dimensions with the ADS vacuum, okay, which was constructed by Luis and Trindle in this work, admit a natural uplift to d=10 type IIB supergravity on an S-fold, okay, through this maximal J-fold model, okay? So this is the reason for this. I will come back to this point by the end, okay? Now let's mention the dual equal-3 superconformal field theory. At least let us mention the proposals for the dual holographic dual of these backgrounds, of type IIB on these backgrounds. Now, a proposal for the dual theory, the dual superconformal field theory, on the boundary of the 4-dimensional anti-de Sitter space was put forward, at least for the n=4 background, by Hassel and Tomasiello in this paper here. They gave 2 equivalent characterization of the dual theory. In one of these characterizations, it is defined as the infrared limit of a 4-dimensional n=4 super Yang-Mills theory compactified on a circle with a monodromy defined by this Jn, so a J monodromy, okay, along this circle acting on the complexified coupling constant of the super Yang-Mills theory. So what is called a duality wall. In another equivalent characterization, it is defined as the infrared limit of the so-called TUN theories, originally constructed by Gaiotto and Witten in this paper, in which an SUN subgroup of the global symmetry group UN times UN, okay, is gauged by the n=4 vectors, and a level n Chern-Simons term is introduced on the theory. Indeed, the theory is obtained by obtained by compactifying the super Yang-Mills on a circle is in the infrared is effectively a 3-dimensional theory. Okay, so on this 3-dimensional theory, this level n Chern-Simons term is introduced, and the n of this level n is related to this monodromy generator, hyperbolic monodromy generator. Okay. So this is a very tentative list of the relevant references related to this the study of this kind of solutions. Okay. I apologize for its incompleteness. Those references, so those solutions which are here described in this pink square, okay, they are all related to the n=4 solution, which is the most important one somehow, through marginal deformations. While those solutions in this brownish square, okay, they are related either to an n=0 solution with SO6 symmetry, okay, which is, if you want, the simplest solution of this kind, okay, but unfortunately it is also unstable, or to the n=1 solution with SU3 symmetry, okay, which is of course stable, being supersymmetric, okay. Okay, so let us now proceed and discuss in some detail the geometry of the half maximal S-fold solution, which was studied in these two references. Now, the background, as I said before, has this general structure where this deformed phi sphere is conveniently described as the product of two spheres, which I denote by S1 and S2, fibered over an interval I. Now, the R symmetry of the ADS4 superalgebra, which is an n=4 superalgebra, okay, of the ADS4 superalgebra is, as you know, SO4. And this is also the symmetry of this solution. Now, how is this SO4 implemented on this geometry? This SO4 is nothing but the product of the two isometry groups of these two spheres, SU2, 1 and SU2, 2. This is the way these two isometries have been denoted here, okay? So this is how this vibration, okay, describing the deformed phi sphere is described, okay. This is a picture of these two spheres fibered over the interval I, and at the endpoints of this interval, one of the two spheres shrinks to 0. But this is related to the fact that these two spheres are not cycles, because of course S tilde 5 has no two cycles, okay? And now the explicit form of our solution, okay, as far as the matrix is concerned, is this one, where alpha is the coordinate along this interval, okay. This is the matrix of ADS4, which is well known. D eta is the matrix on S1, eta being the coordinate along this S1. And remember that there is a monodromy acting on this S1, as we shall see in a moment, okay. Then this d omega I are the measures along each of these two spheres, okay, and they have this expression here where I runs from 1 to 2. Theta I and phi I are the coordinates on each of these two spheres. In particular, remember phi I, these are the azimuthal coordinates on each of these two spheres, okay? So as far as the 4 form is concerned, okay, it has this general form here. Notice that it does not depend on the coordinate of S1, okay? While the 2 forms have this expression, and they do depend on eta, that is on the coordinate of S1. And this is not accidental. Also, the axion dilatons which have this form here, okay, depend on eta. Notice that the dependence on eta is not arbitrary, okay, but only those fields which transform non-trivially under the duality group of type IIB superstring theory have a dependence on eta. The reason is that the dependence on eta, okay, of the fields is described through the action of a twist matrix A of eta belonging to SL2R, okay? Now, this dependence on eta suggests that this background can be also described as a Shirk-Schwarz reduction from 10 dimensions to 9 dimensions on this S1, okay? Now, Shirk-Schwarz reduction, I will come back at the end comment here on this general feature. Now, what do we mean by Shirk-Schwarz reduction? Now, Shirk-Schwarz reduction were devised by Shirk and Schwarz at the end of the 70s, and they are a generalization of the Kaluza-Klein reduction on a circle, or even on some more higher dimensional compact manifolds. Remember that Kaluza-Klein reduction on a circle, in a Kaluza-Klein reduction on a circle of a theory on a circle, we assume all fields not to depend on the coordinates of the circle, okay? While in the Shirk-Schwarz reduction, we assume all the fields to depend on the internal coordinate, that is the coordinate of the circle on which we are compactifying, but this dependence, okay, have to be special, of a special kind. Namely, the dependence has to be factorized in the action of a matrix, satisfying a well-defined condition. In this case, the matrix is a twist matrix in the global symmetry group of the theory, of the higher dimensional theory in 10 dimensions. Okay, so this ansatz is nothing but a Shirk-Schwarz ansatz from 10 to 9 dimension on this S1. I will come back to this point. Now, as we move around the circle, due to this twist matrix, okay, there is a monodromy acting on the fields, okay? The monodromy is expressed in terms of the twist matrix in this way here. The two forms transform under this monodromy matrix, as well as the complexity. Well, here I denoted this the complex combination of the axion dilaton fields by rho, but in fact here I'm denoting it by tau, so I'm sorry I changed notation. But this is the axion dilaton complex field, okay? So everything that can transform under SL2 transforms under this, the action of this monodromy. Now, we are not there yet, because as you can see from here, okay, the monodromy matrix obtained from this twist matrix does not have integer entries, so it's not in SL2Z. Now we want the monodromy matrix to be in SL2Z, because we want to the original, the initial and final backgrounds as we go around this S1, okay, to be virtually indistinguishable from the point of view of type 2B superstring theory, okay? That is to be related by an SL2Z symmetry. This is achieved by acting on the solution that I just showed you by means of an SL2R transformation Gn, depending on the integer n, okay? What we obtain is still a solution, because SL2R is a global symmetry of the classical type 2B supergravity. And if we fix T to depend on n as an arc cosh of n divided by 2, then you can see that the monodromy matrix becomes precisely Jn. Okay, so becomes precisely the Jn element of SL2Z. Okay? Okay. Let's move on. Now it turns out that the vacuum, the four-dimensional vacuum describing this solution, okay, which is an n equal 4 vacuum preserving 32 supercharges, okay, and having SO4 symmetry, is not isolated, but is connected to n equal to 2 and n equal to 0 vacua through flat directions, which I mentioned earlier, okay? These flat directions of the scalar potential, okay? We denote by chi1 and chi2 the parameters, the scalar parameters along these flat directions, okay? Now, these flat directions, as we mentioned earlier, they correspond to exactly marginal deformations in the dual field theory. So these are marginal deformations breaking supersymmetry to either n equal to 2 or n equal to 1, or n equal to 0. Now, this web of marginally connected vacua were uplifted to S-folds of type IIB in this paper here, okay? And let us see how we interpret these parameters from a geometric point of view. Well, these two parameter deformation of the solution can be affected in a very simple way by simply replacing d phi I. Phi I remind you, are the azimuthal angles of the two spheres, okay? By changing d phi I into d phi I prime, which is a combination of d phi I with d eta through these parameters, deformation parameters, okay? Now, this recipe suggests a very simple interpretation of chi I as moduli of the internal metric. To illustrate this, let us consider the toroidal fiber, okay, spanned by the coordinates phi 1, phi 2, and eta. Here I'm talking about a toroidal fiber because this is not a global torus in the internal manifold, since the two circles parameterized by phi 1 and phi 2 shrink at points. So this is really a local description, okay? Of course, because there's no one cycle parameterized by phi 1 and phi 2 in the internal manifold, okay? Now, in the absence of deformations, this toroidal fiber, okay, defined in this way, can be described as R3 divided by a cubic lattice, a lattice generated by mutually orthonormal vectors. Now, in the presence of these two deformation parameters, we can, these three torus, okay, local three torus gets deformed and can be described as R3 divided by a deformed lattice, which is no longer a cubic lattice, but is generated by three vectors, which I show here, two of which are still orthonormal. But the third one is not, and is not orthonormal to the first, is not orthogonal to the first two, but leans towards the first two. And the components of V3 along V1 and V2 is proportional to the two deformation parameters. Now we can parameterize this torus, okay, using coordinates phi 1, phi 2, and eta, okay, along these three vectors, okay. And we can see that the generic, if we write a generic, the position vector of a generic point in this way, in this parameterization like this, okay, being it in this coset, it is defined modulo an element of the lattice, of this deformed lattice, okay? And this implies that phi 1, phi 2, and eta are separately periodic. Phi 1 and phi 2 have period 2 pi, and eta have period t, okay? Now, in this parametrization, as it is well known from the geometry of tori, in this parametrization, the deformation parameter chi1 and chi2 enter the matrix of the torus, of the three torus, okay, through the scalar product of these generating vectors, okay? So the matrix depends on chi1 and chi2 in this parametrization. Now, as it is well known, we can choose a different parametrization of the torus, okay, referred to an orthonormal basis, okay, by writing the position vector in this way through angles, new angles, phi 1 prime, phi 2 prime, and eta, where phi 1 prime is related to phi in this way through this combination, okay? Now, it is well known that in such parametrization, the internal matrix of the three torus becomes independent of chi1 and chi2, because this is an orthonormal parametrization, okay? But chi1 and chi2 occur in some in a non-trivial global identification. Phi 1 prime are defined modulo 2 pi, but as we move around the circle, so as eta goes into eta plus t, phi prime also change, okay, are shifted. So there is a non-trivial global identification. As a consequence of this non-trivial global identification, oblique identification, SO4 symmetry is broken to the U1 squared, to the product of two U1s. These U1 symmetries, okay, are nothing but the isometries acting on the angles phi alpha, the two azimuthal angles, as translations, okay? So this is the symmetry of the backgrounds we will be working with, the residual symmetry. Now, as a consequence from this description, it follows immediately that if we change chi alpha by 2 pi over t, okay, V3 is shifts by an element of the lattice, okay? So we move from one lattice we're still in the same lattice, okay? So this implies that chi alpha, the deformation parameters, are in fact periodic, okay, are in fact periodic. Okay, now within this framework, we computed the Kaluza-Klein spectrum on the solution, okay, the Kaluza-Klein spectrum on the n=4 solution, the Kaluza-Klein states organized in long spin 2 supermultiplets, okay, and the conformal dimension of the highest weight state has this form here with respect to the various quantum numbers. Let us focus on this term here, okay? Now, this 2 pi n over t is nothing but the contribution to the Kaluza-Klein mass, okay, due to higher modes along the S1 direction, okay, the S1 parameterized by eta, okay? Now, from the description, characterization of chi1 and chi2 that I just gave, it follows that in the presence of these deformations, okay, the conformal dimension changes by simply replacing this 2 pi n over t, okay, with this combination of n and the two quantum numbers J1 and J2 associated with these U1 and U2 residual symmetries, okay? Now, J1 and J2 can be half integer, and they are half integer for the spin-Oreo fields, okay, spin 1/2 fields. Now, what this implies is that all masses, if the n=4 solution was perturbatively stable, okay, also the deformed solution is perturbatively stable. Namely, all masses in all Kaluza-Klein, the whole Kaluza-Klein, all scalar masses in the whole Kaluza-Klein tower are above the Breton-Lohner-Friedman bound. As far as supersymmetry is concerned, well, the spin 3/2 masses depend on these marginal deformations, chi1 and chi2, in this way. Now you can easily verify that if for generic chi1 and chi2, none of these masses is equal to 1. Now, in order for a spin 3/2 field to be massless in anti-de Sitter, okay, as an anti-de Sitter field, this mass, which is the Poincaré mass, has to be 1 in unit L to the -1, where L is the radius of anti-de Sitter, okay? Now you can easily see that for generic chi1 and chi2, none of these eigenvalues satisfy this condition. So for generic parameters, the background is non-supersymmetric and has this U1 times U1 symmetry, okay? Which enhances if one of these is 0, enhances to SU2 times U1. However, something special happens when chi1 is equal to plus or minus chi2, because in this way you can see that 2 of these eigenvalues become 1, okay, 1. And this implies that two gravitinos become massless. Now, a massless gravitino implies residual supersymmetry. Okay, so there are 2 supersymmetries in these cases. Okay, and the residual symmetry is still U1F flavor, U1 flavor times U1R, where U1R is a special combination of the isometries defined earlier acting on phi 1 and phi 2, and the same for U1F, the flavor symmetry. The flavor symmetry is defined as the U1 symmetry acting trivially on the preserved supersymmetries, which are 2 in this case. Now, evidence of stability, all these backgrounds, even the non-supersymmetric one, and these non-supersymmetric 2-parameter ones, and this is the interesting feature, are perturbatively stable. Namely, as I said, all the scalar masses in the whole spectrum are above the Breton-Lohner free band bound. Moreover, there's no bubble of nothing, okay, related to possible collapsing of the NS1 and S5. This is the absence of bubble of nothing related to possible bubble of nothing related to a collapsing of S1 is due to the fact that fermions have a non-trivial boundary condition, satisfy a non-trivial boundary condition along this S1, okay? And this protects the solution from a bubble of nothing decay. Preliminary probe-brain analysis show there is also no brain jet instability. So this leads to an evidence of the existence of a non-supersymmetric conformal manifold of the dual conformal field theory. And this would be, the first non-supersymmetric conformal manifold known, at least to my knowledge. Okay. Now, then we have there is also an interpretation of these parameters from the point of view of the dual superconformal field theory. This was for the n equal to 2 vacua. Okay, this has been put forward by Bob Eber, Gautes, and Van Mauden. Okay. And it consists in a shift or a redefinition of the superpotential of the dual theory. Remember that the dual theory is a gauged, is conjectured to be a gauged version in the infrared, a gauged version of the so-called TUN theory defined by Guyot and Witten. Okay, then we put forward a similar interpretation of the holomorphic dual to the non-supersymmetric deformations, okay, by adding to the holomorphic superpotential a non-holomorphic term of this kind. This clearly would break all supersymmetry. Now, it turns out that this is not the end of the story. Namely, apart from these 2 deformation parameters, chi1 and chi2, there is a third one, phi, okay? Now, for chi equal to 0, the 2 parameter solutions n equal are preserve n equal to 2 supersymmetry, okay, and they interpolate between an n equal to 2 vacuum, preserving SU2 times U1 being the R symmetry, SU2 the flavor symmetry, and the n equal to 4 SO4. So there is a larger manifold, conformal manifold underneath all these solutions. Okay, the closed Klein spectrum of these solutions was studied by in this paper by Mattia Cesario, Larios, and Oscar Varela. So let us summarize graphically what we have discussed so far. So this is the point, our starting point, the n equal 4 SO4 theory. Okay, and we have shown that it has a 2-parameter manifold of marginal deformations. Okay, generic point in this manifold preserves n equals 0. Okay. Then, besides these 2, this plane, there is a third deformation, which I described here by this line, parameterized by this phi, okay? And there is this plane parameterized by chi minus, that is chi plus, chi1 minus chi2, okay, with the chi1 equal to chi2, equal to minus chi2, okay? There is this plane here, which which consists of n equal to 2 vacua, okay? So there is a 2-dimensional conformal plane of n equal to 2 vacua. Okay. This can be completed by a parity transformed picture. Okay, but I'm not going to describe this part. Okay. So Kevin, how much time do I have more?
Maybe 5-10 minutes.
Okay, fine.
Start a bit late.
Okay, thank you. So as you can see, let's go back here, which is a bit clearer. As you can see, the phi deformation, this extra third parameter, interpolates between an n equal to 4, our original n equal to 4 vacuum, and an n equal to 2 vacuum with the symmetry SU2 times U1, where U1 is the R symmetry acting on the preserved supercharges, okay, and SU2F is the flavor symmetry, leaving the supercharges invariant. Now, this enhancement of a U1 flavor to SU2 flavor occurs at phi equals 0, okay? Fine. Let me move on. And let me mention the S-fold black holes. So some recent results that we have obtained in this recent paper in collaboration also with Annick Ruder, who is a PhD student there in your institute. So we studied black hole solutions asymptoting a generic point here. That is asymptotic and n equal to 2 S-fold, okay, with U1 times U1 symmetry. Now, in order to do so, since constructing studying a generic solution in the full n equal 8 theory is rather hard because of the plethora of scalar fields which are present in the model. There are 70 scalars there. We defined a n equal to 2 consistent truncation of the n equal to 8 model and studied black hole solutions within this truncation, okay? And here we could use also the known formula for supersymmetric black holes in n equal to 2 models. Now we studied, we classified n equal to 2 consistent truncations asymptoting these vacua, and in particular containing the n equal to 4 vacuum, okay? And the largest of these truncations describes 3 vector multiplets and 4 hypermultiplets. The 3 vector multiplets is this defines an STU submanifold, where the 4 hypermultiplets, okay, define an extension of the STU model, okay? The gauge group is U1 squared times R squared, okay, R being transformations generated by nilpotent symmetries, okay? And this is a subgroup of the larger symmetry group, local symmetry group of the J4 model, okay? Now, what we did was to all these symmetries are isometries of the quaternionic manifolds. Now, what we did was to solve the attractor equations in the n equal to 2, this n equal to 2 truncation, okay, and look for ADS2 times H2 geometries, okay? That is ADS2 times some internal compact geometry, okay, which could describe near horizon geometries. Now, we could find, by solving the attractor equations, we could find 2 solutions. The first class of solution described the near horizon geometries of universal black holes, so-called universal black holes. They are called universal because on these solutions, or these black hole solutions, the scalar fields are fixed. That is, their values are near the horizon coincide with the value at infinity, which is the value at the vacuum, okay, at the chosen vacuum here. In these solutions, the H2, these solutions all have an locally hyperbolic geometry for the horizon, okay? And the radius of ADS2 and the radius of H2 are related in this way. And the radius of H2 is related to the radius of the four-dimensional and undefined Sitter space in this way here. Then there is a second class of solutions, which is particularly interesting. They describe a one-parameter solution. Why there were no residual parameters apart from the gauge coupling constant. There were no residual charge parameters. Okay, they were all fixed. All charges were fixed. Here we are left with one parameter solution. Okay. In fact, there were two parameter solutions, but I will discuss a one parameter solution. Okay, as a one parameter subset of this class. And they describe a solution of this form here with this geometry, okay, featuring a very special kind of scale separation between these two factors, okay? And I don't know if you can see this, but the ADS, so the length of ADS2 is related to the length of H2 in this way here, as 1 over square root of 2 times the hyperbolic cosine of the parameter lambda, parameterizing this class of solutions. Now, the black holes and the one parameter class of solutions, they all preserve one quarter, they are all 1/4 BPS, so they preserve two supercharges. And they were uplifted by us using exceptional field theory. The one parameter class of solutions, only for lambda equals 0, was completed to the ultraviolet as the near horizon geometry of a universal black hole. And the ultraviolet and the vacuum describing the ultraviolet limit is precisely the n equal to 2 S-fold with SU2 flavor symmetry. Okay. In general, the one parameter class describes, it was uplifted to in a 10-dimensional geometry of this form here. That is to an ADS2 J-fold solution with the Jn monodromy along S1. Okay, so this is a new kind of solution, which differs from those which I've been discussing previously, in the fact that the non-compact part now is no longer an ADS4 geometry, but it is an ADS2 geometry. Now, of course, we would like also to have black hole solutions with evolving scalar fields, okay, which are particularly interesting from the point of view of from the holographic point of view and within the problem for as far as the problem of entropy counting is concerned. Okay, so to this end, we should abandon the n equal to 2 truncation and use more general, well, larger truncation, like the half maximal truncation, okay? That is a truncation to a pure half maximal supergravity. Now, we know that such truncation exists, okay, because of general arguments given by and proven by these authors in these works, okay? The general statement is that if a supergravity admits an extended anti-de Sitter space, then it also admits there exists a pure and extended supergravity, that is an extended supergravity describing only the gravitational multiplet, okay, an extended multiplet, describing the same vacuum. In our case, we have a maximal supergravity featuring an n equal to 2 vacuum. So what these people have proven is that there must exist a pure n equal to 4 supergravity, okay, describing the same vacuum. Okay, we are constructing this model, okay, but this is still work in progress. So let me end with some concluding remarks. So we gave a tentative overview of the main issues related to ADS4 J-fold solutions in type IIB superstring theory, namely supersymmetry breaking through marginal deformations, the conformal manifold in the dual theory described by these marginal deformations. I discussed a bit about this, and then I also touched upon the issue of stability of the non-supersymmetric solutions, and the issue of black holes asymptoting these kind of solutions. Okay. Now, as I mentioned earlier, okay, at the beginning, when I started discussing the explicit form of the n=4 solution, okay, these solutions can be obtained within a Church-Schwarz reduction from the n=8 SO6 gauge d=5 theory, which contains this famous background, AdS5 times S5 background, to 4 dimensions with a hyperbolic twist in SL2R. Okay. Now, this observation is crucial because this allows us also to construct S-fold solutions, more general S-fold solutions with different dimensions. In particular, AdS2 S-fold solutions, which is a project that I'm pursuing in a different collaboration here. And we are doing this by compactifying to two dimensions, 3-dimensional gauge supergravities, which features AdS3 vacua. The most important of that is the AdS3 near horizon geometry of D1, D5 system, okay? And the reduction from 3 to 2 dimensions is done through a Church-Schwarz twist in the isometry group of the moduli space of the AdS3 vacuum. Now, here, the moduli space of the AdS3 vacuum is much larger. It's not just SL2. It's the isometry group of the moduli space is not just SL2R, but it is SO4,4. So now the monodromy is an element of a larger duality group. Okay, so now we are constructing S-fold backgrounds, which features a duality, a more general duality transformation. Okay. Then another open issue is to extend the one parameter, the full one parameter family of J-fold solutions that AdS2 J-fold solutions that we have discussed earlier, to a black hole solutions asymptoting AdS4 vacuum. Okay, and finally, it would be interesting to and finally, and this is what I mentioned earlier, the previous transparency. What we are doing now is embedding pure n=4 4-dimensional AdS supergravity, and therefore all its solutions through the maximal J-fold model into Type IIB superstring theory. Okay, and this will be some a new results which allows to uplift a large class of solutions to Type IIB superstring theory, and this kind of uplift for these solutions so far was not known. Okay, to our knowledge. Okay. So thank you for your attention. I stop here.
Thank you.
Are there any questions?
Any questions? Yeah, I'll have to transmit. So, are there any questions? Yeah, or from online. Anybody online wants to ask questions? Okay, since there don't seem to be any questions, let's thank Mario again. Thank you.
Okay, thank you very much for your attention.
Thank you.
Okay, thanks a lot.
Thanks.
Hi, Costas.
Hi, how are you, Mario? Thanks
Hello.
for the talk. Yeah.
How are you? Are you fine?
Yeah, all good. How are you?
Okay.
Good.
Okay, see you then.
Thanks. Bye.
Sorry,
Goodbye.
Prof.
Oh, there was a
Can you
question.
hear me?
Yes, please.
Sorry, I was trying to fix my microphone.
Okay.
With the
Sure.
toroidal vibration, you mentioned
Yeah.
that there are three spheres. But before one of the spheres is parameterized by eta, right?
Sorry, not spheres, circles.
Oh yes, S1s. Sorry, yes, S1s.
Yes, right.
Is that sphere playing the role of an interval in the original setting? Because in the original setting, you had an AdS5 cross a tilde S5, and then there was that S5 was fibrated
Yeah, this one.
Right.
You mean interval?
Yes, on that so is that interval playing the same role as the S1 with an eta parameter?
No,
in this case?
No. This interval is part of the S tilde 5. Now, you see S tilde 5 multiplies S1. So S1 eta is this one. So this is the S1 eta. Okay, this is the S1 eta. Okay.
Okay.
So if you want to visualize these three circles, which the torus is made of, one is this. One is this. And the other is outside this picture here, is this one.
I see.
Okay.
Okay.
So one is this parameterized by phi1. The other is this parameterized by phi2. Okay. Clearly, none of these are cycles because they shrink at points, you know, and the north and south of these two spheres. So none of these are cycles. But locally, we describe them as cycles. Okay. So 1, 2, and then there is this external S1. Okay, which does not fit in this picture as tilde 5. Okay, it's external S1. This S1 is a true one cycle. Okay, so this is the only true one cycle in the story. Only true one cycle that is unshrinkable one cycle. All the others, they do shrink. This is the only one cycle. Okay.
Okay. Thank you so much, Prof.
Thanks to you. Are there any questions? Okay, so if there are no other questions, I thank you for your attention, and thank you for inviting me to give this seminar. Goodbye.